Thank you all for returning. uh, so yesterday I made this point that non-perturbative characterization of the standard topological insulator is that if you probe this system by inserting a magnetic monopole, that it acquires the charge which is shifted from an integer by a half. Right? And I also argue that that's a unique property of an insulator made out of electrons, which are of electric charges, which are fermions, and a Cramer's doublet under time reversal. Right? So this is where I stopped yesterday. I asked the question whether this charge G over 2 on a probe monopole is only possible for the standard topological band insulator. Is this a unique characterization of the topological band insulator, or are there other phases of matter that have the same property? Right? And I asserted that there are in fact 4 distinct time reversal symmetric topological insulators with spin orbit coupling, where this probe monopole has charge E over 2. So only one of them is the standard topological insulator, and the other 3 require interactions. Okay, so let me start from here and tell you a little bit, particularly for the sake of any experimentalists that may have bravely come back, how to characterize these other phases and what sort of materials one might be thinking about for them. And after that, I'll unapologetically move on to more theoretical things. Okay. Right. So in some sense, I've already answered this question. So the zeroth order question that we started with, whether topological band insulators are distinct from ordinary insulators in the presence of electron-electron interactions, the answer is yes, they are indeed distinct. Right? And the next question is whether in the presence of interactions there are new topological insulating phases that cannot be described by band theory, right? Even as a matter of principle. Right? And the answer is yes, there are new phases, and in total there are 6 new phases which are beyond band theory. Right? And the questions that one may want to ask are, okay, if I'm asserting that there are 6 new kinds of phases, what are their physical properties, and where should experimentalists look? Right? Okay. Yeah, so the total list is this total of 8 phases. The 6 are the 6 that are not contained in band theory. And yeah, it's exhausted. That's all there is. There's this many and no more.
How do you know that? How can you be sure that some other probe will not see some other?
Right. So this is not just based on monopole. So I haven't told you how we obtained this result. I throughout these lectures, I have not planned to tell you how we obtained these results, but what I was planning to do was to build up the theoretical thinking that the chain of reasoning that leads to a result like this.
I see. But I just wanted to understand what is the input into, let's say some mathematician has proved the result.
Yes, actually a mathematician has proved the result.
But he needs some input.
Right.
What input goes into it?
Right. So the input here is the following, right? So we declare that we are interested in electrical insulators first. So to say that something is an insulator, of course you need electric charge, right? So there's charge conservation, there's charge U1 symmetry, and we say that there's spin orbit coupling, which means that there's time reversal symmetry, but there's no other symmetry, right? So we know the symmetry group. There's a charge U1, and this which is unitary, and there's time reversal, which is anti-unitary, and we know that the electric charge is even under time reversal. So the group, there's a specific group structure, then it's U1 semi-direct time reversal. So that's the group structure. And furthermore, we know that electrons are Cramer's doublets under time reversal, so they transform projectively. So the answer is different if they were Cramer's singlets. Right? So this is for real electrons, which are Cramer's doublets. So that specifies which microscopic system we are thinking about. Right? Now the other parts of the input that goes in is to say that it's a topological insulator, it's a symmetry protected topological insulator, meaning there's a bulk gap, and all the excitations in the system are trivial. They're electrons or composites made out of electrons, right? So that's the input, nothing else.
And then mathematics, sorry to interrupt, but the
Yeah.
mathematicians classify all possible partition functions as a function of, what do they classify? All possible partition functions as a function of background gauge fields or something else?
They do something more complicated, which, so they don't think about things directly in terms of partition functions. They think about theories in terms of maps from the Hilbert space of states. You think about the path integral and you imagine slicing up the path integral in various ways, and this path integral is defined in some space-time manifold. You slice it up in various ways. Each time you slice it up, there's some vector space of states. And then you think about the path integral as defining a map between, if you slice it up here, and then you may allow it to do this and so on. So there's a vector space associated with this slice, that slice, and so the path integral defines some map between all that, right? So, and you want to consider this for some arbitrary manifold that you've chopped up in some ways, and you want to, so for them, the field theory is defined by a space of maps such as these.
And you're
right?
a topological field theory.
Exactly, it's for a topological field theory, and with it's the most specific thing that they do is to classify what's called an invertible topological field theory, which is a slight generalization of an SPT phase. It includes things that are chiral and so on. You know what the word invertible means? All right, but then they have a way of classifying these things, right? Yeah. Yes, the standard topological band insulator.
So you don't mean like Mott insulators having a topologically protected system?
When I say topological band insulator, I just mean a band insulator. But these lectures are about topological insulators beyond band theory. So some of the states that we are describing will be Mott insulators which have protected surface states.
So that in interaction you mean the spin-orbit?
No, the spin-orbit coupling is just something that, that's not the interaction. The interaction is Coulomb interaction.
So in the previous slide,
Yeah.
this, I think electron in presence of interactions means what?
In presence of interactions means electron-electron interactions. Coulomb repulsion, yeah.
Okay, how it is distinct? That's the thing I don't know. Because for example, like DI equation and so on.
Sorry?
DI equation.
Yeah, yeah,
So these are all simple insulator.
right.
No electron-electron interaction.
No, in real life, everything has electron-electron interactions. It's an approximation to treat it as though there's no electron. It's a fantastic approximation. And the conceptual question is whether the distinction between topological insulator and trivial insulator is an artifact of that approximation, or whether it's true even beyond that approximation, right? So one of the conclusions in yesterday's talk was that it's not an artifact of that approximation, and even beyond the band theory approximation.
What I mean is that to get this topological band insulator phase, you don't require electron-electron interaction. I mean, this
Absolutely, that's right. That's absolutely correct. But having gotten it without electron-electron interactions, the question is if you add electron-electron interactions, which are there in real life anyway, then is it still a distinct phase of matter, or is it really not distinct, right? So that was the question for yesterday, right? And so that's one kind of question. Now the other kind of question is whether there are new phases that that cannot be described even as a matter of principle within band theory. And what I'm asserting now is that there are 6 and only 6 new phases which are beyond band theory. Okay? All right. So the statement then is that within band theory, the classification of such insulators is there's a Z2 classification, meaning there's precisely two kinds of insulators. There's a trivial band insulator and there's a topological band insulator. Now, beyond band theory, once you include interactions, the statement is that Z2 becomes a Z2 cubed classification, right? So, as Shiraz was asking, I'm asserting the statement to you. I'm not giving you a proof. So, the physics proof is, so we gave a physics argument for this statement. But since Shiraz asked, now mathematicians have confirmed the statement, right? So, it was a good check for both the physics argument and the math framework that they gave the same answer, right? Because the line of reasoning is completely different, right? In fact, we can barely understand each other. Though I drew some pictures, I don't really know what I was talking about here.
And the physics argument is what you summarized at the end of your last lecture.
No. What I summarized at the end of the last lecture was just for this part, right? So I'm happy to go over the physics argument to you, but perhaps I should do that maybe in tomorrow's talk towards the end, right? Because I need to build up some methodology before we get to, right now I just wanted to throw this result out just to get people interested, particularly experimentalists, right? So, so Z2 cube means that there's now 8 phases, a total of 8 phases which satisfy these conditions, that they describe electrons with no symmetries other than time reversal and charge conservation. And there's trivial insulators in the bulk, meaning there's no exotic excitations in the bulk. But nevertheless, they have non-trivial boundary states. And they're not smoothly connected to each other. So one of these 8 phases is the familiar trivial band insulator, like silicon, right? Now, another of these 8 phases is the familiar topological band insulator, like bismuth selenide or any of these things. But then the yeah.
You said the symmetries were charge conjugation, time reversal.
Charge conservation, time reversal.
Okay. Time reversal and parity as well?
No. We don't need parity. But time reversal acts on the electron. The electron is a Cramer's doublet under time reversal. So T squared is -1. So that's very crucial. Okay. So what about the remaining 6 phases, right, which are beyond band theory, right? So some of these are described very simply. To answer your question, you imagine the electrons, because of Coulomb repulsion, have formed a Mott insulator, right? Now, once they form a Mott insulator, the active degrees of freedom are spins, right? And now, imagine the spins have formed a symmetry protected topological paramagnet, which is now protected just by time reversal, right? So this is the analog of the Haldane spin chain phenomenon, but now in 3 dimensions. Okay, so so some of these other phases which require interactions should be viewed as topological paramagnets in 3 dimensions, 3D generalizations of the Haldane chain phenomenon. Okay, so they can't be described within band theory, just like the Haldane chain. You can't describe within ordinary band theory, right? So you have to go into a Mott insulator and do something. So similar things happen here, and these are some of these other phases. Okay.
Sorry, are there simple physical models, and probably the answer is yes, for all the 8 phases? Or are there some which?
There are models. How simple they are. It's a matter. It's in the eye of the beholder. There are concrete models that one can write down for all 8 phases. Yeah. Okay. So at this stage in the lectures, I don't want to give you the proof for the Z2 cube classification. Rather, what I want to do is describe the physical properties of some of these new states. In particular, if you're an experimentalist, what's an experimental characterization of these new phases that you will know tells you that it's distinct from the standard topological insulator. Okay, so let me illustrate this with an example. We're going to talk about physical properties and I'll illustrate it with an example, with two examples in fact. So how to tell an experiment? Suppose there's a correlated insulator. Maybe it's samarium hexaboride, maybe it's something else. You probably don't have a favorite correlated insulator. Yeah, I know, but he's a field theorist, but there must be someone in the room with a favorite correlated insulator. Maybe it's, I don't know, yttrium iridium oxide or something. And you know that it's an insulator, and some guy comes and tells you, oh, it's an exotic kind of topological insulator, right? And you're an experimentalist, you don't believe the person, you ask him, what should I do, right, to test the statement, right? So the general idea always is that so to probe the non-trivial surface states, we imagine explicitly breaking symmetry at the surface to produce a simple state. And then we can study that simple state and see if that simple state has some non-trivial property. Okay? So in this case, the symmetries that we have are time reversal and charge conservation. If we want to break time reversal, we should deposit a ferromagnet at the surface. If we want to break charge conservation, we deposit a superconductor at the surface and proximatize and induce superconductivity at the surface, right? And both of these, both of these things, both of these protocols give unique signatures for the standard topological insulator. Okay? So now we can ask what happens within these protocols. What's different if you have this new interacting topological insulator? Okay. So let me illustrate this for two of the allowed topological paramagnets. I'm going to call them 1 and 2. Okay. So let's ask what happens if we deposit a ferromagnet at the surface of such an insulator, right? So let me remind you what happens at the surface of the standard topological band insulator. Okay? So this top thing, so this story is just the standard story from 10 years back about the topological band insulator. So if you deposit a ferromagnet on top of it, you break time reversal symmetry, and then what you can do if the time reversal symmetry breaking is strong enough is to gap out the massless Dirac fermions at the surface of the topological insulator, right? And that gives you a state with a quantized electrical Hall conductivity. But the novel thing about this induced quantum Hall state at the surface of the topological insulator is that the quantization of the Hall conductivity is half of what's allowed in 2 dimensions. Sigma xy is a half, okay? Even though there's no fractional charge or anything, right? So it's fractional Hall conductivity without fractional charges, right? So the real way to probe it is to imagine forcing a domain wall in the ferromagnet, right, where the magnetization points in one direction here, up, in the down direction here. So then there's a domain wall, and then at the domain wall there's a one-way, there's a conducting channel which goes one way, right? There's an edge mode that goes one way. This edge is the same as the standard edge of the 2D integer quantum Hall state in 2 dimensions, right? So that's the story. That's the standard story about the topological band insulator. Now, yeah, this is the topological insulator. This is just the surface.
So you have 2 ferromagnets separated by something.
Sorry?
This top layer.
Yeah.
So why you show these 2 domains separately?
Oh, I'm just imagining that think about a semi-infinite slab, right? And then deposit of, so this is my topological insulator surface, right? And the Ti goes into the bulk. And I deposit a ferromagnet on top and create a domain wall, right? That's what I'm showing there. And at the domain wall, there's a one-way current carrying edge mode, right? So that's an old prediction, basically from the original Fouquet and Meillet paper. It's related to things that you might have heard, but this quantum anomalous Hall effect that many people have seen in magnetically doped TIs. That's another way to do the same experiment. Yeah.
When you say deposit a ferromagnet, do you just mean turn on a magnetic field that sort of is coupled to the surface? Or
Right, but you could do that, but since we these are practical matters. Since you want to create a domain wall, and it's very hard to reverse the orientation of the field on the just at the surface of a tiny sample, what you really imagine doing is to have a ferromagnet, and then the orientation of the magnetization is, you could imagine, just for historical reasons, that the ferromagnet formed with the domain wall nucleated. Right. There's even in the absence of a magnetic field that, but the ferromagnet creates its own magnetic field. But then you could imagine creating a domain wall that it formed with the domain wall nucleated.
no, but I'm missing something. Why did you need the domain wall? Isn't it enough to just have a magnetic field on the surface and then you get Landau levels in that field?
Right, but how do you probe that Hall conductivity of that? Right. So the real meaning of this half Hall conductivity, a very precise meaning of this half Hall conductivity is in terms of what happens at the domain wall. That's right. So if you wish, so if you wish, take a semi-infinite slab, right? So this is the TI and this vacuum, right? And we're going to deposit a thin layer of a ferromagnet. And the magnetization of this ferromagnet is, say, pointing this way here and that way there. So then there's a domain wall, right? Now, this is a two-dimensional thing. So from a view like that, right? So the view like that, you have this kind of picture. So this is the domain wall. And this is a ferromagnet with magnetization up, ferromagnet magnetization down. Then at this domain wall, there's a conducting edge mode. So everything else is an insulator. Right? The bulk is an insulator, this is an insulator, this is an insulator, but there's a conducting edge mode, and it goes one way. Right? And that edge is the same as the edge of the 2D integer quantum Hall effect.
You characterize topological insulators by the fact that they conduct on the boundary, right?
Yeah, but now we are forcing the boundary to become an insulator by depositing a ferromagnet. And in the absence of the domain wall, the ferromagnet is, the magnetic field from the ferromagnet is such that it gaps out the metallic electrons. Right? So that's, at least conceptually, that's the protocol. Okay? No. This is just standard band theory physics. Right? Yeah. Okay? So I think this statement, if you've not seen it before, it's maybe surprising, but it's a really cool statement. So if you've not seen it before, I urge you to see it now. You're seeing it now, but to understand it, it's pretty cool, right? It's a cool phenomenon. But conceptually, let's now ask, if you take one of these new topological insulators, which require interactions, and you do the same thing, what will you see? Okay? Now, for one of these topological paramagnets, there's an amazing prediction you can make that you see nothing. Right? I don't know, this may look strange to you, but usually when theorists tell experimentalists that you should see nothing, they don't get very excited. So this looks like sort of a useless statement, but you should recognize that even though you should see nothing, the fact that you should see something for the standard topological insulator means that if you see nothing, you at least know that it's not a standard topological insulator. Right? It may still be a trivial insulator like silicon, and you have to distinguish it from a trivial insulator. That will come in the next slide.
And sorry, just in terms of what you said at the end of your talk last time, is it because you don't have that John-Simons term with that wrong quantization at all?
Yes, that's absolutely right. So, or equivalently in the bulk, the theta angle is 0. Exactly.
So it's like you put two of them together.
Exactly, that's right. Now, for the other topological paramagnet, it turns out that there is something at this domain wall. It's not that it's totally dead and gapped. There is something, but what there is not an electrical current, but just a neutral current, okay, which can transport heat, but not transport electricity. Okay? And just to intrigue the string theorists, I put in some exotic words. Everyone else can ignore that. That's exactly what it is. It's the boundary. So this is described by an E8 level 1 CFT. So, but it's electrically neutral. It will transport heat. That's what it is. So this experiment can clearly distinguish these three kinds of states.
It's a Westmino-Witten model at level 1, based on E8 at level 1 on the boundary?
That's right. That's exactly right. I can explain that in great detail later, but let me not scare the experimentalists right now. Okay, so the natural question to ask is, this experiment clearly distinguishes, for instance, this state from both the standard topological band insulator and from the trivial band insulator, right? But this state is, not seeing anything. How do you distinguish it from a totally trivial band insulator, right? So you need some other characterization, some other experiment. So let's turn the other knob. Let's forget this experiment completely, or let's say this is done by one class of experimentalists, and then we go to another class of experimentalists and tell them, don't deposit a ferromagnet, instead deposit a superconductor, right? And we'll see what happens, okay? So now, again, let me start with the standard topological band insulator and ask what happens if you deposit an S-wave superconductor right on top of it. This, again, was contemplated by Fu and Kane in a classic paper 10 years back, which many of the experimentalists here probably know very well. So what it does is, if the superconductivity leaks into the metallic surface, it will gap out the electrons at the surface of the topological insulator. It will pair them up. There will be some proximity-induced pairing. And this resulting gapped surface superconductor, the vortices in the superconductor have 0 modes, which are Majorana fermions. Right? So this observation of Fu and Kane launched all the recent search for Majorana fermions in condensed matter, Majorana 0 modes in condensed matters, in a condensed matter context. So let's ask about the fate of the similar experiment on these topological paramagnets. Okay? So now it turns out something remarkable happens. So I take my topological insulator and I deposit an S-wave superconductor on the surface, and if the proximity coupling is strong enough that I gap everything out, right? Or rather, normally I would have gapped everything out, right, in the standard topological insulator. But here, what you end up getting is a gapless superconductor with nodal quasiparticles, just like, for instance, in the famous high TC superconductors. And the number of gapless nodes here corresponds precisely to 4 Dirac cones or 8 Majorana cones, which are protected by time reversal symmetry. And that's something that a photoemission experiment can detect. Right? So it's a weird experiment. You take this surface of, say, this topological paramagnet 1. In its pristine state, it's gapped. The bulk is an insulator. The surface is an insulator. So how would you know that it's doing anything weird? You deposit a ferromagnet, form a domain wall, try to look for something, and nothing happens. But then you deposit a superconductor, and boom, it becomes gapless. Right? So it's really bizarre effect. Right? Because if you're an experimentalist, you have to have a really good reason to want to do these experiments on any specific material. Right? So somebody needs to make a very strong case that that material may actually be in a phase that does these interesting things. Otherwise, it would be a huge waste of money. But as a matter of principle, these are characterizations of this phase. And
These gapless states are the interface states.
absolutely, yeah. Right?
On the interface.
That's right.
The interface of the superconductor with the topological.
Exactly, yeah. Right? So this kind of thing gives you a unique experimental fingerprint for all these 6 new faces, should they exist in some particular material? Should any of them exist in some particular material? Okay?
So there are already gapless modes in the boundary of your topological parameter, right?
No. So initially, this guy, we have no idea what that state may be. It may be gapless, it may be gapped, all those are possibilities. But we are depositing the superconductor to get a simple state.
But given that you're claiming that it's in an SPT phase,
Yeah.
don't you want a gapless?
No, we just want a non-trivial surface. But the surface may be non-trivial by having a gapped topological field theory in the surface. And a priori, we have no idea what it does.
Sorry, I have a related thing, which is you had 3 possibilities on your previous.
Right.
This is the one where nothing happened.
It happens for both.
It happens for both.
It happens for both.
And it's the same thing.
You get exactly the same thing.
Both for one.
Sorry?
No, you said that. Both.
Yeah.
But is it necessary that you need to have SOFs conductors?
If you have some more weird superconductor, then disentangling the weirdness of the induced state from the weirdness of the superconductor that you put in is going to be problematic. It's better to take a simple known superconductor, put it, and then see, and then anything weird that happens, is a property of the surface state. Right? Yeah.
So what is a nodal superconductor?
A superconductor where there are gapless Fermi points, gapless, in this case, minor fermions. So it's gapless just at one point in K space. In a usual metal like copper, the electrons are gapless on an entire Fermi surface. So here it's just a Fermi point. That happens in say the high TC superconductors and so on. Okay, so continuing with the part of the talk where I don't apologize to experimentalists. Right? So let's go towards the question of which materials should we be thinking about. Right? Experimentalists are most interested in this question usually, but there's also the question that's hardest to give satisfactory answers from theory. Topological band insulators, I think we all got lucky because the theoretical framework is very well established, it's very predictive, it's just band theory. Now when you're talking about correlated materials, it's very hard to be very predictive in a very confident manner. So the best we can do is to give some guidance on where interesting things may happen, right? And then there has to be dialogue with, theory experiment dialogue for it to move forward. Okay, so we only have some vague guesses for which materials might be interesting to look at. So let me give you one direction where something interesting probably happens, right? And that is to look at frustrated spin-1 magnets in 3 dimensions. Okay. Now, in general, there's a lot of work on frustrated magnetism, quantum magnetism in diverse dimensions, but a lot of the focus has been in studying spin-half magnets on grounds that they are most quantum, so they'll do the most interesting things. Right? Now, spin-1 magnets are also strongly quantum and could be strongly frustrated. And the claim here is that perhaps they also do something equally interesting, and perhaps they are good playgrounds to look for SPT phases. Okay? Already in one dimension, we know that the one-dimensional spin-half antiferromagnetic chain forms a super exotic state. It forms a gapless spin liquid. But the spin-1 chain forms an SPT phase. Okay? So similarly, in 3 dimensions, one can make the case that a frustrated spin-1 magnet is a possible platform for one of these topological paramagnets. And it's a very simple picture for a ground state wave function in such a case, which I'll just sketch.
Why do you talk about Haldane chain systems? What is the difference between spin-half and spin-half chains?
For a spin-half Haldane chain, it's gapless.
Okay.
right?
Have a gap in the magnetic excitation.
That's right. Spin 1 chain is gapped,
Yeah.
right? And the spin half chains are even more exotic than SPT phases. But spin 1 is just as just at the right level of exoticness.
Really help in this case.
What do you mean?
Gap in the spin excitation spectrum.
No, by definition, as we declared that we're only going to talk about phase with the gap in the excitation spectrum for everything, right? There are many more interesting things in the world, but for these lectures, we're going to restrict ourselves to, so saying yesterday, we forbid our phase from doing anything interesting that we knew about before and see whether it still has some life in it. So imagine you have a diamond lattice magnet with spin 1 sitting at each side of the diamond lattice with frustrating interactions. So normally the diamond lattice is bipartite, so people don't think about it as frustrated. There's natural nail ordering pattern, up-down nail ordering. But it turns out that if you have a little bit of second neighbor interaction, then the diamond lattice antiferromagnet is extremely strongly frustrated. There's no unique classical ground state, and all kinds of things happen. That's been known for a long time. Now, the diamond lattice, sorry, I'm inflicting a lot of serious solid state physics on you guys. But crystal structure is the part of solid state physics that I think makes most field theorists become field theorists. Anyway, so diamond lattice consists of two interpenetrating face-centered cubic lattices. Okay, that's an interesting fact. So let's label these two FCC lattices, the A and B sublattices. So what we're going to do to write down a wave function is to imagine close packing this FCC lattice, each FCC lattice with loops. Right? So each loop, a close pack means that every site of the lattice is visited once by a loop. Okay? And then at each site of the lattice, we have a spin 1 magnetic moment. So for each such loop packing, we just let the loops, the spin 1s in the loop form a Haldane chain. Okay? And then the ground state wave function will take it to be a sum over all loop configurations with some phase factors. And the phase factor will choose to be such that when an A-type loop has a non-zero linking number with a B-type loop, so it does that, then there's a phase of -1.
So what are I see, corresponding to the
two sublattices, right? So that's the wave function, right? So all the interesting topological information is in this phase factor, okay?
And this is a good variation of the wave function?
We don't know. It's very hard to calculate because it has minus signs. But we can write down mean field theories which produce the state. We can construct the state, right? And it's very hard to do energetics. It's in 3 dimensions. Numerics is hard. Analytic theory is hard. So we have to rely on experiments, right? So the only thing we can say is that this may be interesting. So let me skip this thing. So we
You said close back with loops.
yeah.
Now there's a choice in how to do that?
There's infinite number of choices, right? So there's infinite number of loop configurations. We're going to sum over all loop configurations.
You're going to sum over all ways of close packing with loops?
Exactly, that's right. Now, for each such loop configuration, there's a phase factor which is purely topological. It's -1 to the linking number of these two species of loops.
And 2 different ways of close packing with loops are weighted with the same relative modulus, but just
Exactly. Yeah, we could change the modulus. It doesn't, so long as the modulus is spread out, the wave function is delocalized in loop space. It will be in the same phase. But
sure.
yeah. Let me skip why this actually works. There's some nice pictures that you can draw to explain why this works, but let me skip that. And let me ask, okay, so there's some reasoning, right, that perhaps spin 1 magnets on a diamond lattice may be a good place to look for interesting topological phenomena in a magnetic system. So then,
You have some intuition for setting up this kind of wave function.
Absolutely, yeah.
I don't understand that. Could you?
I didn't. I skipped that slide. So the point is this, right? So let me take a couple of minutes because I wanted to get to the next slide, which was mainly to motivate some materials people to study some things, right? Actually, can I come back to this slide after the material slide? So this line of reasoning, we're just hunting in the dark, right? So that leads us to a guess that it's interesting to study frustrated quantum magnets with spin bigger than 1 in 3 dimensions, right? Perhaps on a diamond lattice. So that's the only message really from all this theoretical thinking. Now, you look around in the literature, we did, and we realized that there is a class of materials.
Sorry, why did spin have to be bigger than 1? You could have found these Haldane chains.
No, Haldane chain is for spin 1.
Yeah. But I mean, in 3D, I thought
Yeah.
the idea was you do a similar thing in 3D,
That's right.
but you only expect something interesting for spin bigger than 1, or am I missing?
No, spin half is also probably interesting, but probably does something even more exotic than an SPT phase.
No, I mean, what about spin equal to 1 exactly on this diamond kind of?
That's what you're thinking about. Spin equals 1 exactly.
Oh, that's what you're thinking.
Exactly.
Okay. I
That's
thought
right.
you meant spin greater than 1. Okay.
No, greater than half.
Greater than 1. Okay, sorry.
Right? A lot of the attention from the magnetism community has been on spin half systems. We're trying to push people to look at spin 1 systems, right? Saying don't give up, spin 1 may also be interesting. Right? So there's a class of spinel oxides. How many people in this room have heard of the word spinel? Good, there's some materials people. Of course, you've heard of spinels. If you go to any museum of natural history and you go and look at gemstones, maybe 1/3 of them are either spinels or pyroclores. It's actually quite amazing. They occur quite frequently in nature. Anyway, so materials of this form, AB204, where the A side is magnetic and the B side is non-magnetic, are interesting 3D frustrated magnets. And the A side forms a diamond lattice, and the exchange paths are such that the second neighbor interaction is actually quite big, and they are strongly frustrated. And there's a cobalt aluminum oxide and a manganese aluminum oxide, which are spin 3 halves and spin 5 halves, frustrated magnets on diamond lattices in 3D. So the natural thing is to ask whether it's a spin 1 example. And initially, I was very excited. I thought nickel aluminum oxide will do the job because nickel is usually spin 1. But unfortunately, it doesn't work. And the material exists. Chemists know about this. But once I started talking to people, someone did something and concluded that nickel and aluminum have the same atomic size, so they exchange positions. Real life intervenes. Yeah, so the nickel, instead of sitting at the A side, likes to sit in the B side, right? So this does not work, though the material exists. But then there's this person, Terrell McQueen at Johns Hopkins, who was very brave and didn't give up. And he managed very recently to synthesize nickel rhodium oxide with nickel at the A site. And he sees that it's a paramagnet, but we don't know if it's a topological paramagnet. Right? So that's where things stand. So the materials people here, the main thing that I would perhaps hopefully motivate you to do is to keep your eyes open for frustrated spin 1 magnets in 3D and see if you can make some interesting such magnets. All right. We don't know what they'll do. Yeah. So if you can make a transition metal pyrochlore magnetic insulator, that would be interesting. There exists one such material, which, but anyway.
You should tell this to me later because it's too embarrassing to ask it. I thought the idea of frustration was to just have some kind of triangular lattice where you can't satisfy everything.
Right.
Why do you have to do something so exotic? Just take the underlying spins to be integer instead of half integer. Choose your lattice configuration suitably and get frustration with That's not enough for.
Right. So that may be enough. The question is, what can we, you can put spin ones, if you're a theorist, you can put spin ones on any lattice you want, right? But then you have to make some guess on what the model will do, right? For this diamond lattice, nearest, first neighbor, second neighbor interacting model, there's at least a mean field theory that suggests that it will be in this topological paramagnet phase, right? But it's a mean field theory, so we don't know how accurate it is, right? There are other mean fields which will give you other states, right?
Since it's a mean field theory at best, maybe experimentalists brave enough just construct enough frustrated integer spin.
That's what they should do. They shouldn't take anything else that we say that seriously. Hopefully all this is just serves as inspiration to some experimentalists to play around and look for spin 1 frustrated magnets and take their focus a little bit away from spin half frustrated magnets. That's the sales pitch that I want to make. All right. So that's all I wanted to say about things that may be vaguely connecting to materials and experiments and so on. From now on, I want to talk more about formal theory. Right?
That sounds always
Shiraz, I can quickly answer your question. Oh, I can just tell you separately. I mean, there's some nice pictures that you can draw. So actually, let me skip this. I can just tell you separately. All right. So just for completeness, let me also say, and we're going to lead on to the next topic, from a practical point of view, what we really care about in terms of strong interactions or standard topological insulators, right? The standard insulators with, of electrons with spin orbit coupling, blah, blah, blah. But if you're theoretically minded, you could ask the question about the fate under interactions of all free fermion or non-free or free fermion SPT phases. Everything that has been classified, topological superconductors, this and that. And there, the full classification of within free fermion models, there's this full classification of topological insulators and superconductors with any symmetry due to these people from many years back. Now, what's the fate under interactions? Okay, so the analogous question, but for all these other symmetries. For many physical symmetries, that these we now understand what happens with interactions. In many cases, we know that some free fermion topological phases are not stable to interactions, and in some cases, we know that there are new topological phases with no non-interacting counterpart. Okay, so what I'm going to do, from now on, is to talk about theoretical ways of thinking that have been useful in obtaining the results that I've mainly asserted so far. Okay, sort of build up the way of thinking that helps you confront the kinds of questions for which I've just given you the answers till now. Okay. So it's very useful in sort of building up a way of thinking to start not with the problem of electrons, not confront that head on first, but instead think about SPT phases of bosons or spin systems. Right? No fermions in the Hilbert space. Okay? And so why is this useful? Right? It's useful because, first of all, there is no free particle limit in which we can sensibly describe a gap phase of bosons. Right? Non-interacting bosons, the only thing they can do is Bose-condense. Right? So unlike for fermions, therefore, right from the beginning, we had to think non-perturbatively. Right? So it forces us, it jolts us out of the comfort zone of free fermion band theory right from the beginning. Okay? And in general, experience in strong correlation physics tells us that correlated bosons are much easier to understand than correlated fermions. Right? The boson-Hubbard model we basically understand as completely physically as we want. The fermion-Hubbard model we hardly understand beyond 1D. Right? Fermions just make the problem hard. So let's start with bosons. So there's been tremendous amount of progress in understanding these bosonic SPT phases from various points of view. First in one dimension, and in some sense this entire story of SPT was started several years back by these papers, and particularly want to highlight this paper by 4 people, 3 of whom were postdocs or something at that stage, and the other person was a not that senior, so which more or less pioneered this entire body of work, thinking about the Haldane chain in a bit more detail than people had done in the previous 25 years. Then a lot of big name people followed up later. This classification based on very formal techniques. Group cohomology is a word that is thrown around quite a bit. Cobordism is another word that's thrown around quite a bit. Somewhat simpler classification by Ashwin Vishwanath was actually very useful early on, just based on abelian Chern-Simons theory. At least as part of my personal history, I found this accessible compared to anything else in the literature. And there's physics-based discussions by many people, and I'm going to talk about this physics-based understanding primarily, with one example each in 2 dimensions and in 3 dimensions. Okay?
Sorry, you go on, but just in general terms, are these different ways of classification equivalent, or are some finer than the others?
Yeah, so good. So it's these 2 things can be usefully compared. That's right. So in space dimensions less than 3, so 0, 1 or 2, these 2 things give equivalent answers. Now in 3 dimensions, group cohomology misses a phase and cobordism finds it, right? And so cobordism, at least in 3 dimensions, is more general than group cohomology. Now, I'm not sure about the status beyond 3 dimension. There are arguments, people in the field argue about which one is better beyond 3 space dimensions. I've totally ignored. I wonder why, yeah. Again, the physics-based approach is get everything right, I should say. So I think I personally, since I don't understand either group cohomology or cobordism, I prefer cobordism because it agrees with all the physics-based things. So, yeah.
What is the bosonic and the fermionic SPT phase?
Oh, it's a question of what your underlying particles are. If your underlying particles are bosons, it's a bosonic phase. If your underlying particles are fermions, it's a fermionic phase. Now, the next question you should ask me, but maybe you won't ask me, but you should ask me, is what does it mean to say what the underlying particles are? Right? There's a long philosophical debate between the high energy and condensed matter community. I don't see why. It's in condensed matter physics, when you ask what the underlying particles are, we know exactly what they are, right? If you take a solid state person and they were studying, bismuth selenide, the underlying particles are clearly electrons, right? Or you take a cold atoms person and they have rubidium atoms in their trap. Their particles are clearly bosons. It has nothing to do with any theory that we write down or anything. It's what we put into the system, right? I think high energy theorists often assume that the fields that appear in the Lagrangian are the underlying particles. Not all high energy physicists, but
We should go on. But
we should go on.
the underlying particles, even in your case, may not be electrons, but it doesn't matter. It could be strings, but it doesn't matter. And so that's why
we also believe in effective field theory a lot more than you guys do. All right. But this is a great question. I've had a lot of confused arguments with high energy physicists because of totally different meanings of the words underlying particles. Right?
Is there, apart from cold atoms, is there any real material where the underlying particles are boson?
Oh, every spin system, right? If your lattice model, if the good effective model is a spin Hamiltonian, spins at different sites commute. So that's it. Okay, so I'm going to talk about a very simple example in 2 dimensions. Some of this may actually be accessible to experimentalists. So I'm going to ask the following question. Can bosons show an integer quantum Hall effect? Right? Usually, when we talk about the integer quantum Hall effect, we talk about electrons that have filled a full Landau level. Now that's clearly, the act of filling levels is something that fermions do because of Pauli exclusion. But for bosons, you never talk about filling levels, right? Free boson theory, you just put all the bosons in the lowest state, right? So any discussion of an integer quantum Hall state of bosons must necessarily happen in not in a strongly interacting context, right? And so to talk about this integer quantum Hall state, well, so what do we mean by integer quantum Hall state, right? The first thing we should mean is that the Hall conductivity is quantized to be an integer, okay? Common sense, right? But we want to mean something more than that. The electronic integer quantum Hall state has no anyons as excitations, no fractional charge, no anyons. So we're going to demand that not only does this state have an integer quantum Hall conductance, but that it also has no exotic excitations in the bulk, right? So my underlying particles are bosons and the excitations are the same bosons or composites of the bosons, okay? No fractional charge, fractional boson number, nothing.
Normally, an integer quantum Hall state normal topological phase instead of SPT phase.
Sorry?
Usually integer quantum Hall states are described with Chern-Simons series which are normal topological phases, right?
Normal topological
Like
phases.
not SPT.
They're not SPT, that's right, for electrons. We'll see that for bosons, there is an integer quantum Hall state, which is an SPT. Okay, so I'm going to describe a specific model which shows this phenomenon. And by studying this model, we can understand the structure of a two space dimensional SPT phase in some detail. Okay? So we'll take 2 species of bosons, each at filling factor nu equals 1. So filling factor means this, the ratio of number of particles to number of flux quanta. Okay? If you wish, you can think of a bilayer system, like in bilayer quantum Hall states. So each boson moves in this magnetic field, and we let the bosons interact with each other through some 2-particle repulsion. Okay? So the external magnetic field is curl A, and each rho I is the density of species I. Okay, and this is the Hamiltonian, it's not the Lagrangian. If you were to write down a Lagrangian, there'll be a linear bi dagger dt bi. So it's not relativistic at all. Okay? So what are the symmetries of the system, right? So the way I've written this Hamiltonian.
Self-interactions are only between the two species. Is that right?
No. So Vij is some general matrix. Later on, it turns out it's enough to just consider delta function repulsion. So it's very simple, right? No disorder. Mu is a chemical potential. Right? You can add disorder and so on, but you don't have to at this stage. So it's 2-component bosons in a strong magnetic field. This system, 2-component bosons, cold atoms people work with all the time. They don't yet know how to get a strong magnetic field. People are working on it very hard. But the main reason to study this at this stage is not so much that it's realizable in an experiment, but it's because it's a simple model that will teach us something about the general structure of phases of this kind. Okay, so as I've written it, the model has conservation of the number of bosons of each species independently, right? So there's two global U1 symmetries associated with the conservation of both N1 and N2. And no other symmetries. Time reversal is broken by my external magnetic field. Okay? So N1 and N2 are separately conserved. Equivalently, we can form these combinations which I'll call total charge and total pseudo spin, N1 plus N2 and N1 minus N2, which are also conserved. Right? And the charge current, when I say there's a charge current, what it'll mean is that N1 plus N2 is transported, so both particles move in the same direction. Pseudo spin current means that there's no net transport of N1 plus N2. The two particles move in opposite directions. It's a counterflow current. Okay? Now later, we'll relax this to conservation of just the total boson number by allowing bosons to tunnel between the two layers. Okay? For the time being, let's just ignore the tunneling. Okay. So, so this is an example of how condensed matter physicists often solve problems. We'll write down a Hamiltonian, write down a model, and we'll then write down the answer. Okay? That's one of the most important methods in condensed matter physics. Okay? So we'll write down, of course we don't know anything for sure, we'll just guess the answer.
Yeah,
right?
I thought the trick of the trade, you write down the answer and then you invent the Hamiltonian, for which it is the answer.
That's also something that, those are all trade secrets. So let's guess a possible answer, right? So let's assume, there's various the parameters in the Hamiltonian are the Landau level spacing and the strength of the various interactions, the same species interaction and different species interactions, right? Now let's imagine a situation where the interspecies repulsion is not small, that it's reasonably big. So then what the particles will want to do is, because the two species repel each other, the two particles will want to stay away from each other, right? That's what that term tries to do. In the quantum Hall context, what this, this suggests a wave function where you build in a zero of the wave function whenever a particle of type 1 approaches a particle of type 2, right? So the natural guess is that the wave function has a factor like this, Zi minus Wj, which forces it to vanish whenever any Zi approaches any Wj. Okay? And then, there's usual Gaussian factors associated with the lowest Landau level. Okay? So this is a guess. We don't know if the guess is, at this stage, we don't know if the guess is right. But we would imagine that such a phase where the avoidance of the two particles from each other is incorporated through such a factor in the wave function, that such a phase probably exists somewhere in the phase diagram. Let's implement this more formally.
So if you ignore this repulsion term,
Yeah.
then this describes all particles of type 1 in the same state.
If I ignore the V12 repulsion,
Yeah, ignore the Zi minus omega j.
right,
So,
then I have nothing, right? Everything else is dot, dot, dot.
it's dot dot dot, and the exponential is just the same for all.
It's the same, that's right, yeah.
It's like a Bose-Condensed, one particular.
No, it's not, this is not, this by itself is not a legitimate wave function. It's not a Landau level wave function. Landau level wave functions are polynomials of Z, and yeah.
But I thought, isn't there one which is just one?
Isn't there one with just, actually there is. So that's right. So there is one with just one, and you could put all the particles in that state. Right?
So ignoring that, it's that, and then there's some spread out.
Exactly. But that state is infinitely degenerate because you could have put it in any of, the Landau level is infinitely degenerate, right? You could have put it in any of the Z to the M states, right? And so it's not physically correct to think about it as spreading out, right? Okay, let's take this idea seriously and try to implement it formally to obtain some effective field theory of the phase that may be described by this kind of wave function. Okay? So what we should do, as we are taught in quantum Hall physics, is to implement this kind of thing through a flux attachment procedure. Okay? Basically, what this factor tells us is that if I fix the coordinates of all the W particles and take any Z particle all the way around any W particle, then there's a vortex in the wave function. Okay? So the wave function winds by 2 pi, which means that particles of each species, according to this guess, see the particles of the other species as a vortex. Okay? So that's what I said here. So the standard implementation of this physics is through a flux attachment procedure, where we attach one flux quantum of one species to each boson of the other species. Okay? And this flux attachment, so instead of working with these original particles, which are shown in either red or as dots, we work with these transformed particles, which is this original particle plus an attached flux. Okay? Now, with this kind of flux attachment, each one of these new particles now moves in a net magnetic field which is on average 0. The external field is cancelled exactly by the attached flux. Okay? And furthermore, these new particles, one can argue, are bosons. If you attach the flux of the same species, it will change the statistics, right? Make it into a fermion. But you're attaching a flux of a different species, so it doesn't change the statistics. It's still a boson. So at the end of this flux attachment, we would have transformed the system to a system of new kinds of bosons, which on average see 0 flux, and then you can just condense them and get a state. Okay? So those are words, but let me describe it formally with some equations. Okay?
Sorry, just to understand, there's of course one underlying magnetic field.
Right.
But when you do the flux attachment, we think of a flux for each species, is it?
That's right, yeah. That it will become clear from the field theory, right? Because this, right now, what I'm writing here is exact. It's an exact transformation of the original Lagrangian. Now I've shifted from Hamiltonian to a Lagrangian. Okay. So what we've done is to replace the original Lagrangian with the B fields and the external background A field, traded it instead for a theory in terms of this B tilde field, right? The B tilde field differs from the original B field by having an extra coupling to these gauge fields alpha I, okay? And these alpha i's, their dynamics is described by our Chern-Simons theory. There's a mutual Chern-Simons term. It's this really longhand for alpha 1 d alpha 2 over 2 pi. Okay? Now, why does this work? Right? So if you take the equation of motion of, say, alpha I 0, vary this with respect to alpha I 0, varying with respect to alpha I 0 here gives me Bi star Bi. So it's the number of these I particles. Varying with respect to alpha I 0 here gives you the flux of alpha 2 divided by 2 pi. So this means that there's a flux attachment equation that tells you that curl of alpha 2 over 2 pi is equal to rho 1, and vice versa. Okay? So you built in this flux attachment in the Lagrangian. Okay? And at the level of wave function, this corresponds to a gauge transformation on the many body wave function, which builds in this flux attachment. It's a rewrite in this gauge transformed basis. Okay? This is very standard in quantum Hall physics, in theory of quantum Hall physics.
So in your old Lagrangian, you didn't have any of these fluxes. You just had the V's.
Exactly.
So this is new physics, right?
It's not new physics. So here I have new fields Bi tilde, which are related in some complicated way to the original fields Bi.
You're saying that there's a field redefinition that takes this to the original Lagrangian?
Exactly. There's a field redefinition.
I see. I don't understand how it.
Let me just write it out explicitly.
Isn't the point that
don't know if this is clear. Let me just rewrite it here. Okay. So this factor, so this is the density of the other species. And this number, I choose it to be just the angle, right, of x minus x, of the vector x minus x prime. So, no, e to the 2 pi I times some number times the density. Now, the density is conjugate to the phase. So, what this does is to shift the phase of this field by precisely this amount, right, everywhere. Right? So, what it does then is to attach a vortex of this other species rho 2 to the first guy. Now, after you do this singular gauge transformation, right, you can plug this into the Hamiltonian and you just end up deriving this.
Sorry, I should go on. Can't you just think of integrating out the Chern-Simons fields, alpha 1 and alpha 2?
You could do that. Yeah, it's equivalent. Yeah, this is exactly equivalent to this. Right? So if you take the equation of motion, the equation alpha I 0 appears linearly in the theory. Right? So it's just a constraint that constrains the flux of these the magnetic flux of these gauge fields to the particle density.
So it's a non-local field redefinition.
Exactly. That's right.
Takes you from one state.
Exactly. Okay. So this part is exact. But then what, and it's also completely standard. This is, from the late 80s, early 90s, adapted to the present problem. Right? Flux attachment mean field is a standard tool in studying quantum Hall physics. So these alpha i's are Chern-Simons gauge fields, and this is a mutual Chern-Simons term that implements flux attachment. Okay? So now, because of these conditions, the average value of the Chern-Simons, of the flux of the Chern-Simons gauge field is exactly the same as the average density of particles. And because the filling fraction condition that each species is at filling fraction nu equals 1, the average flux of the internal gauge field is the same as the flux of the external gauge field. So I can cancel these off against each other in a mean field description. Right? And then so there's a mean field in which I take the average value of these fields to cancel the external A, and then these B tilde I fields now move in zero field. Then I've tamed the quantum Hall problem. Right? Now I have particles moving in zero field, and then they just condense. Okay? So that's the framework to describe. So the guess for the wave function is to inspire this field theoretic framework. Exactly. That's the mean field state. It's not an exact statement, but it's a mean field state. But in that mean field state, we can ask about the physical properties, and we can ask about the Lagrangian for a probe U1 gauge field. Now, there's an A1 and an A2 that couple separately to the two conserved currents. So I'm not going to do the algebra, but the answer is that there's again a mutual Chern-Simons term for the background probe gauge fields. Okay? Now, if you now rewrite this in terms of the charge and current and pseudo-spin counterflow response, this corresponds precisely to an electrical Hall conductivity of sigma xy equals 2 and a pseudo-spin Hall conductivity of minus 2. So this is an integer quantum Hall effect for bosons.
So if I diagonalize the Chern-Simons term,
Right.
Under this diagonal Chern-Simons term, each of your two bosons transform as bifundamentals?
Bifundamentals.
The charges under each of the two diagonals?
Exactly. That's absolutely right. Yeah.
So the two bifundamental bosons.
Right.
And the k is equal to 1 and minus 1. Is this right?
2 and minus 2.
2 and minus 2.
But there's also a gluing condition. There's some, they're not totally independent, right?
Because of some
Yeah.
flux capacity.
Exactly, yeah. So in equations, this is the description of the state. Now Mandar is still here, so I felt like I should give a more physical description as well. Okay? Well, physically, it turns out to be very simple to understand what's going on, right? With just drawing some pictures. So the particles that have Bose condensed are this composite bosons where I take my physical boson and attach it to a flux with the other species. Now let me drive a current through the system in the y direction. Okay? So these particles are what carry the charge. So if I drive a current, these particles have to move. Right? So let's say I drive a current of species 1, then the particle that will move is this bound state of the particle 1 and the flux of particle 2. So it's the current of this object. Right? Now when this object goes in this direction, since it's dragging along this flux of particle 2, there's going to be a voltage drop of species 2 in the transverse direction. Right? By somebody's law, I always forget whether it's Faraday or is it Faraday? It's one of those. When you move a flux in a field, there's a transverse. It's one of those ancient people, right? So that's all there is to it. So that gives you this first equation, and similarly, there's the second equation, and that's the transport in this state. And then you can take the sum and difference and end up with sigma xy is 2 and sigma xy is minus 2. Okay? So this is an integer quantum Hall effect for bosons. Okay? But let's ask about the edge states. Right? Now the fact, so you can see this in many different ways, but sigma xy equals plus 2 for the electrical Hall conductivity means that there must be a charged edge mode going one way. But sigma xy is minus 2 for the contour flow Hall conductivity means that there must be a neutral edge mode going in the opposite direction. Okay?
Say that again, sorry. So the sigma xy for the, so can you just
Right. Can I say it perhaps in a field theoretic way first, and then you can translate it back to.
This seems simpler even to me, but go ahead.
All right. So the point is sigma xy is plus 2 for one u1, the diagonal u1, one of the diagonal u1s, and therefore there's a charged edge mode which goes one way, and then sigma xy is opposite for the other guy. So there's a contour flow mode going the other direction. From the point of view of the Chern-Simons theory, yeah, so the central charge is of opposite sign, right? So there's no chiral central charge here.
Parity conservation. I mean, you could flip the two.
Yeah, we'll see that it's not parity conserving because of the symmetry, right? So the interesting thing is that there are counter-propagating edge states. So unlike in the standard integer quantum Hall effect of electrons, where there's only a one-way edge mode and nothing counter-propagating, here there's two counter-propagating edge states, but only one mode transports electric charge. The other mode is neutral. Okay? So that's why it's not quite parity preserving, because the symmetry realization is such that one mode carries charge, right? And that's anomalous from a field theoretic point of view. You have a right mover and a left mover, but the physical global symmetry is only carried by the right mover, right? So that's anomalous. So the theory is not anomalous, but the symmetry realization is anomalous, right? So that's the weird thing. That's the interesting thing about this PT phase.
I mean, in terms of the Chern-Simons description, you have two Chern-Simons theories, and if you do parity and you flip the two, that's a symmetry.
Exactly.
But you say
That symmetry is not compatible with the way microscopic symmetries are realized in the theory. Only one branch, the right mover carries electric charge. It's a chiral realization of a physical global symmetry.
but the electric charge was, say, the sum of the two.
Exactly, yeah.
But the difference with the two also is a physical quantity, right?
But it's a different one.
It's a different quantity.
Exactly.
But it's a physical quantity.
It's a physical quantity, but now I'm allowed to break that thing by allowing interlayer tunneling. of the bosons.
So you'll allow to break that. Okay.
That's the next thing I will do, right?
That will introduce the breaking. Otherwise, if you exchange those two
Right, that's right. But let me allow myself to break that symmetry. The question is whether I'll destroy these edge states. And the answer is that I won't. So long as charge conservation is preserved, I can't scatter a right mover against a top mover to a bottom mover. Right? Charge conservation prohibits backscattering. Right? So even though the edge states are non-chiral, there is no backscattering for symmetry reasons. Right?
One preserves the symmetry.
Exactly. Right? So all I need is charge conservation to preserve this edge state structure. But if I break all symmetries completely, then there's nothing to prevent backscattering with, say, impurities or something like that, and then I can localize the edges and nothing interesting will remain. Right? So this is why it's a symmetry protected edge state. Right? Now, condensed matter physicists like to describe non-chiral edges like this by saying that the thermal Hall conductivity is 0, and the motivation for that terminology comes from the fact that electrical current is transported just by this charge mode, but everything transports heat. Right? So if you measure the thermal Hall effect, which means you have a temperature gradient this way and then measure the heat current that way, in this state, that's quantized to be 0. In the standard integer quantum Hall state of electrons, it's quantized to be an integer. Right? But here it's quantized to be 0.
Sorry, I got confused. I thought I thought you could have heat transport here without charge transport, because the two could go in opposite. Your pseudo current
Right.
will not carry any charge, but it
Right.
can carry heat.
That's right.
So I thought, then why is your thermal?
In the Hall channel,
Yes.
right, you want one-way transport of the quantity for which you want the Hall response.
You want one way. You don't have one way.
We don't have one way for heat. We have one way for charge, but not one way for heat. Okay? So this is what I already said. We can include interspecies tunneling, and then the pseudospin is not conserved, but the counterpropagating edge modes are preserved so long as total charge is conserved. Okay? So it's interesting to write down the topological field. So what I wrote down so far was the response theory. But what is the topological field theory? And it's a two-component Chern-Simons theory, which is very easy to derive from the story that I described earlier. It's really A1 dA2 over 2 pi, which is a very simple two-component Chern-Simons theory. It has a unique ground state on all closed manifolds, blah, blah, blah. But what's novel is the coupling of the external background U1 gauge field, how it couples to this theory. It couples this way.
And that's because charge was dA.
Exactly, that's right. And that's carried by both species, right? And this, it's easy to check, gives you a sigma xy, an induced Chern-Simons term for this external background gauge field, which is precisely 2, right? Which was the electrical Hall conductivity of 2. And furthermore, this Chern-Simons theory is non-chiral. It's A1 dA2 over 2 pi. So that's a non-chiral Chern-Simons theory. So there's no thermal Hall effect. Okay? And this connects to what Ashwin was doing with general Chern-Simons based classifications of these states. Let me maybe skip this. Actually, I've just been talking. I haven't been looking at the time. Someone should tell me to stop talking.
In string theory, the tradition is that you can go up till 150, but I think the experiment has been safe. You guys you actually have lives starting when? If you start at 11, you can easily go up to 115. Sometimes I have to beg Shiraz that we end at 1:45. So you should decide when you want to end.
No, I'm happy to keep talking till whenever someone asks me to stop.
Well, let me just ask her, are you going to
Let me tell you what I plan to do, at least for the next few slides. I was going to talk about wave functions, and it was a mixture of field theory, models, some numerics, and some general arguments before. That was all in preparation to go further into more field theoretic things later. Tomorrow, yeah. Or today, depending on when. Yeah, feel free to leave whenever, and feel free to tell me to stop whenever. I'm happy to go on, I'm happy to stop, I'm totally flexible.
As I said, usually in the string community, the cutoff is like 1.
All right, okay.
You guys should decide.
I guess it can continue. I don't really think, because the discussion can still go on.
Right, right.
Yeah, I'm curious to hear what, other than the field theoretic stuff you have to say.
All right, yeah. So the next few slides are not particularly field theoretic. There'll be some small mentions of field theoretic things, but
Sure, if you want, you can structure it so that.
yeah, that's what I tried to do for the first half of the talk, but I did promise that there'll be a transition. All right, so the naive guess that we made is actually for the wave function, right, which is Zi minus Wj times these factors, these Gaussians. It turns out it's not quite right, though it captures the right topological physics. It's not right for microscopic reasons. You just study this wave function, and it doesn't want to form a uniform state. It wants to phase separate. Right? And that's easy to check using tricks that Laughlin invented for studying wave functions like this, so-called plasma analogy.
What is phase separation?
Phase separation means imagine if the repulsion is very strong between the two species of bosons. There's a very dumb state that nature might want to make. Right? Put all the type 1 bosons on this side and type 2 bosons on that side. Right? That way they don't repel each other at all. Right? And this wave function, as I've written it there, that's what it wants to do.
But does the Gaussian phase try to keep it inside?
No, it's the Landau level is highly degenerate, right? So you change the filling factor locally, and locally it becomes a nu equals 2 state of bosons, and that will do something, right? But it forms locally it will form an incompressible state, but it avoids the repulsion very cleanly without any need for theorists. Just avoid each other spatially, right?
There's no penalty to going to nu equals 2 here, right? Because it's bosons.
Because it's bosons, exactly, that's right.
You've got twice the filling nu equals.
Exactly. You will pay, if the same species repulsion is large, you pay that energy. But in the limit that the interspecies repulsion is the biggest term in the Hamiltonian, that will dictate all the rules, right? In any case, this wave function wants to do that, right? And this is a well-known problem for wave functions of this type, known in standard fermionic quantum Hall states, say nu equals 2/3 and so on for a long time. And Jane, who's a big expert, one of the pioneers of thinking about quantum Hall wave functions, long ago told us how to fix problems like these. Just include some other factors that build in this repulsion between bosons of the same species, right? So these are what's known as Jastrow factors. It's something that stabilizes this kind of state against this problem of phase separation, right? And there's a rationale for putting in precisely these particular factors as opposed to other things. Again, it's standard quantum Hall stuff, goes back to Jane from more than 20 years ago, right? So this then is a candidate wave function for the state that we're interested in.
Just to back up something
Yeah.
I should have understood, but embarrassing. But anyway, the fact that this wave function, if you stripped off the Zi minus Wj, all bosons
Yeah.
are in the same state,
Right.
this is the same as the statement that the B tilde oscillator is condensed.
No. So the
Why is this wave function the same as the condensate of the B tilde oscillator? The post condensate of those.
wait, I'm just blanking out. So the statement you made was what?
Well, it seemed to me that B tilde was sort of getting rid of the Zi minus WJs, roughly speaking.
Right, yeah.
So
So,
wave function for the B tildes would be the same wave function without the Zi minus WJs.
right. So what you're saying is almost correct, but I really want these factors, right?
So before
Which don't change the topological information, but which still, so essentially this is the wave function of a boson superfluid.
I see. But before
Right.
we get to this new complication,
Yeah,
in just
right.
your formal transformation, if I took this wave function and wrote it as a wave function for the B tildes,
Right.
would that be essentially stripping off the Zi minus WJ?
That may be correct, I'm not entirely sure. But, you know, at the formal level, I don't know the answer. But if once you make this transformation, and then you put this B tilde in a superfluid state, right? What's a legitimate wave function for that superfluid? And the wave function is this guy, right? Or some modification. You need some such factor. Otherwise, it's not really a sensible wave function. I guess that's what I'm trying to say.
I see.
Uh,
So one more.
yeah,
The condensate, the B tildes was just uniform out of a space, right?
that's right. So this state phase separates, so it doesn't quite satisfy that, right?
Okay.
So the stabilization is given by factors of this type, right?
But sorry, just to go back to the comment you made about the fact that physically you expect the wave function to phase separate when the interspecies repulsion is big.
Yeah,
You're saying this is a good wave function when the interspecies repulsion is there but not very big.
exactly. That's right. Yeah. So we'll see exactly where this works in a minute. But yeah. Okay. A little bit of field theory before we go back to the models. This is actually useful field theory. You know, there's useless field theory and there's useful field theory. And this useful field theory, at least for me, this observation was very useful towards models and microscopics. So the edge theory for the state, which has one chiral boson going that way and one chiral boson going this way, it turns out it's a familiar conformal field theory. It's the same as what field theory is called the SU2 level 1 WZW theory. So this the edge theory has an emergent pseudo-spin SU2 rotation symmetry. Okay? Now that then suggests that the state itself is stabilized by a Hamiltonian that builds in that symmetry, right? You know, the symmetry is anyway emergent at the edge. So to encourage the state to form, you build that symmetry into the Hamiltonian, so maybe the state will form, okay? And we can also show that the wave function that I wrote down on the previous slide, this one with these particular factors, is actually a spin singlet wave function for the bosons, right? If you think of the bosons as two components of a spin half, this wave function is you can show as a spin singlet, okay?
So this SU2 is SU2 are mixing the two bosons.
Exactly, yeah.
Do you still have separate conservation for each boson number, or have you broken that?
If you have SU2, then you of course do, right? Because you have charge U1, and then the SU2 means that SZ is conserved. SZ is this pseudo spin, right? So SU2 is implying even more, right? So which then suggests a really simple Hamiltonian that will stabilize the state, right? So for these two body repulsion, let's just take delta function interactions, right? And if we tune the strength of these delta functions to be equal to each other, then the Hamiltonian has a pseudo spin SU2 rotation symmetry. Okay? So it's really an extremely simple Hamiltonian, delta function repulsion, right? And then we can study this numerically, just diagonalize it exactly on a torus, on a sphere, and so on. And people have done that, and one of my collaborators did that. So did Jane, and and there are several groups that did that. And the answer looks really nice.
So you can exactly, even though it's just a delta function, it's a non-trivial interaction, but you can exactly solve the
No. You can numerically diagonalize it with some number of particles.
n particles or something.
N particles where n is 18. That's the state of the art, right? Maybe by now it's 20. So let's ask about the phase diagram as a function of this ratio of these two interactions, GD over GS, right? So GD is G different, GS is G same, right? That's the way to remember. So if G different goes to infinity, right? That's when, you know, this trivial solution of phase separation works, and then each boson species locally is in nu equals 2, and we don't know what really that system does. It's very numerically it's very hard to study, and but there are states that people have suggested that bosons at this filling fraction perhaps form a non-abelian quantum Hall state. That nu equals 2. So that's a candidate state, but we don't know if it's realized. But we do know numerically that it's definitely phase separated here.
And sorry, just it does something interesting because of the remaining GS interaction.
Exactly, that's right. Now if GD is 0, then the two layers are totally decoupled from each other. Each layer is bosons at nu equals 1, and there's a lot of evidence that it's so it's decoupled, right? Now bosons at nu equals 1, there's very good numerical evidence that they form a different non-abelian quantum Hall state. It's a so-called Moore-Reed state. It's the simplest non-abelian quantum Hall state, not for fermions, but now for bosons at nu equals 1. So it's two decoupled, you know, Pfaffians. The wave function is a Pfaffian, so it's called a Pfaffian state. So this is a really exotic state. It has non-abelian anyons. This is phase separated, but it may also be very exotic. In comparison, the state that we are proposing near the SU2 symmetric point is almost totally trivial. There's a unique ground state on all manifolds, no anyons, but it's just that little bit interesting for us to be interested in it. It's an SPT state. You know, I was explaining this to Liang Fu, my colleague, and he said, oh, before we did the numerics, and he said, the state is bound to be there. Murphy's law, the simplest state is always the one that's stabilized. There was a competing state that people had proposed here, which was a non-abelian state. Yes. So every state that anyone had dreamed of for this system was non-abelian. But then, when you do the exact diagonalization, my own involvement was to encourage my talented collaborator to do the numerics, and it's the simple state that wins, and it's very robust. You know, it's stabilized here, but it's very robust in a wide range of the phase diagram, right? So this boson integer quantum Hall state really seems to exist in this very simple model over a wide range of parameters with a big gap and everything. And it's very easy to tell in exact diagonalization on a torus. This state, each Pfaffian has a ground state degeneracy of 3 on a torus. So the Pfaffian plus Pfaffian has a degeneracy of 9. This non-abelian spin singlet state that was proposed here also has some very high degeneracy. I forget what the number is, it's 15 or something. While this state is a unique ground state on a torus, right? So it's very easy to check. And there's other things that quantum Hall people know how to do, like shifts on a sphere and so on. And everything works. So the evidence is quite strong that the state is actually realized. Okay.
Sorry, again,
yeah.
I don't understand why the system has a gap.
Why does it have a gap?
Yeah, I mean, you've got a bunch of bosons, you add one more boson to just go in one of the other states. I know there's some self-repulsion.
Let's
say we go to this side. So the two
here?
are totally decoupled.
Right. Why does it have a gap?
Yes.
Right. So you know, so you have this highly degenerate Landau level, right? So you shouldn't think in terms of non-interacting particles at all. That's extremely far from the correct answer, right? In fact, you know, the real formulation of the problem is that you project all the interactions just to the lowest Landau level, and there's no kinetic energy, right? And you just have two-body repulsion, right? There's no zeroth order starting point in this problem, right? And so where is intuition going to come from? So you have to, the system has to find some way of splitting this many-body degeneracy, right? And one intuition that people have is to tame this complicated problem by doing this flex attachment thing. Right? Now, for bosons at nu equals 1, if you did flex attachment, then you had to attach one vortex, so the same species to each boson. Then you get fermions in zero field. So fermions in zero field will form a Fermi surface. That's a composite Fermi liquid. But then that composite Fermi liquid has a pairing instability. Okay? And that leads you to this paired quantum Hall state, which is a non-abelian state. So that if you want an intuitive answer for why the bosons do what it is, this is the answer.
Let me ask again. Is the gap special to nu equals 1? If nu was 0.9, there still be a gap?
Oh, if nu is 0.9, the system will, it's very delicate what the system will do. Now in real life, not so much for bosons, if you could ask the same question for electrons. Right. Electrons at nu equals 1/3, it's well known there's a gap. What if it is 1/3 minus 0.01, right? No, there's in real life, there's a very simple answer. And the real life answer is that there's disorder in the system. And because of disorder, any extra charge that you induce into the system just gets localized, just gets pinned on impurities. System is still, in the bulk, it's still an insulator, right? Now, if you don't want to be in real life and you just want to answer the theoretical problem in the absence of disorder, then the answer depends very delicately on exactly what rational number or what your closest rational number is. Right? That's Ned.
And the answer would be similar for bosons.
Yeah, this part of the story is similar for bosons and fermions. Now in practice, we don't worry about this kind of thing at all, because with disorder, you'll just pin any extra charge. Right? The question of exactly what happens if your filling fraction is some number nu, which is close to but not exactly a simple rational fraction, is not a physically relevant question. Right? Okay, so before we get to any field theory, there's one more physics point that I want to make.
But at least the strength of the gap will be larger at nu equals 1 than nu equals.
Absolutely, that's right. Yeah. Then that's exactly why it's not a physically relevant question. You go to nu equals, I don't know, 109 over 110. Right? In principle, there will be a different state. In fact, it's a state known as the Jane state. It'll be described by a different topological field theory, but the gap will be so small that in practice it doesn't matter. Okay, the state that I described as sigma xy equals 2 and thermal Hall conductivity of 0. Obviously, I can construct any state with sigma xy being any even integer and kappa xy equals 0 by simply stacking on top of each other, right? Taking many copies of the same state. So you can ask whether sigma xy can ever be odd for bosons, for a boson integer quantum Hall state. And the answer is that it's not possible. And for bosons, the integer quantum Hall state necessarily has sigma xy an even integer. Okay? So why is that? So it turns out there's a ridiculously simple argument for why this is true. So let's imagine that bosons have formed some integer quantum Hall state, where, let me remind you that by integer quantum Hall, it's my definition. It's not only sigma xy an integer, but there are no non-trivial excitations. Right? Now let's imagine, this is the kind of thing Laughlin did in his very first paper on the fractional quantum Hall effect. Let's imagine threading in 2 pi flux through some solenoid that's piercing the sample. Okay? Now when I thread in 2 pi flux, there's an EMF that's induced around it. Right? And in response, there'll be a charge current that flows into the system, right? Because of the Hall effect, right? So you thread in flux. Imagine you slowly ramp up flux through this thing, phi, which goes from 0 to 2 pi as a function of time. Then there's an induced EMF this way, right? And then there's an electrical current in response to this voltage, right? So there's a J. And so there's a net charge that is sucked in, and the charge that is sucked in is given precisely by sigma xy once the flux reaches 2 pi. Okay. This was what Laughlin used to argue for fractional charge in the 1/3 state. This, the beautiful argument that led him to predict fractional charge in the fractional quantum Hall effect. Now this object, once it's sucked in this charge of sigma xy, you can ask what its statistics is, and the statistics is pi times sigma xy. It's a simple argument when you braid two of these things. Now there's no topological order, meaning no exotic excitations in the bulk. Then all the bulk excitations must be bosons. Right? They can't be anyons, they can't be fermions, which means that pi times sigma xy must be an even multiple of pi, right? Which means sigma xy must be even. Right? So that's the simple argument. Okay.
In a sense, doesn't it sort of beg the question whether you can get exotic topological order?
You certainly can. Nu equals 1, there's this Pfaffian state. Nu equals half for bosons is a Laughlin state with semyon excitation. So you can certainly get much more exotic things. So the point here was we forbid all the exotic things and see whether you can still get anything. And yeah.
Then sigma xy is even.
Exactly. And kappa xy is 0. You can ask whether kappa xy can be different from 0 at all. It turns out the answer is yes, but only if it's a multiple of 8. And that's where this E8 business comes. Okay. In terms of physics type things, that's all I wanted to say. What I was going to do next was to put this in a field theoretic framework. Okay.
Maybe we take a 2-minute gap in this.
No, that's all I really wanted to say. So we could maybe take a break after this and move on, or
But will you cover? Because I would certainly like to hear this, right? Because it'll.
right. So let me say this.
Because I don't know if you'll have time tomorrow to go over this. Because
Right. So let me say this right now. So in this particular example, let's ask what happens if we study the response of this SPT phase to a background U1 gauge field and a background metric. Right. So we had the original B fields, and then we do a path integral over the action of the B fields, but with a background A field and a background G. Probe fields, a background probe field A, in addition to the background external magnetic field, but then an extra probe field, and then a background metric which we allow to be arbitrary. And the non-trivial physics of the SPT phase is in the phase of the partition function. Right. So what we want to do is to integrate out all the dynamical degrees of freedom and study the long wavelength induced action for this for A and G. Okay. Now, since we are interested in universal topological properties, we can even take the limit in which the bulk boson integer quantum Hall state is such that the gap to all excitations is taken to infinity. Right. So it's really nothing dynamical. There's no dynamics that you're going to induce for the background gauge fields by integrating out the B. But you will introduce topological terms, right? So the answer for the boson integer quantum Hall state is that there is an induced Chern-Simons term which just gives you the Hall response, right? And this coefficient is precisely the electrical Hall conductivity. So K over 4 pi with K even. And the evenness of K is just the even integer quantization of sigma xy. And in particular, there's no gravitational Chern-Simons term that's induced. That could have happened, right? What's the structure of a long wavelength induced effective action for A and G, right? You could have had a Maxwell term, but that only, first of all, if at all it's there, it's going to contribute to the modulus of the partition function. And second, if you take the mass gap to infinity, you can't induce a Maxwell term.
Suppressed by 1 over gap.
It's suppressed by 1 over gap. right? So let's take the gap to infinity. Who cares, right?
Yeah, but there could have been a gravitational.
There could have been a gravitational Chern-Simons term. The statement is that there isn't, and that's the statement that kappa xy is 0. Okay?
In the model that you studied, that showed us in more detail,
Yeah.
this K was 2.
Exactly.
You already showed us before.
That's right.
But sorry, Senthil, now the thing I don't understand as well enough is, so you have a mass for this B field. I mean, this showing that you don't get the gravitational Chern-Simons term and you get exactly 1 over 4 pi. How easy is that? I mean,
Oh, it's
an interactive theory and so on. So what is
right, but I just argued for you what these numbers were, right? I told you sigma xy is 2 and
is that argument for me was you had a wave function.
no, it doesn't rely on the wave function. It relies, if you wish, just on this picture. So long as you accept this description of the edge state, these numbers are fixed. You know, sigma xy and kappa xy is fixed. Sigma xy is non-zero, kappa xy is 0. Or if you,
The reason I'm asking is if this was a fermionic field theory,
yeah,
then through some standard determinant kind of arguments one might.
right. So if you wish, you can start with this model. This is the effective topological field theory, and integrate out the A1 and A2 fields, right? And that will, the claim is that that will generate this level 2 Chern-Simons term for AC, but will not generate a gravitational Chern-Simons term.
But I mean, the fact that, so I can see from here how to do it, I'm sorry, but if I started with the original bosonic theory with the self-interactions and so
Yeah,
on,
yeah.
is it all robust? That,
Right. So what we are describing from, in terms of going back in the field theory description, you know, doing all this, so this was exact, right? And then we made a mean field approximation, right?
that is what I was trying to ask, is the final result dependent on that or not?
Right. So what this procedure gives us is a description of a state, and the only thing we can hope to get right are the universal properties of the state, right? So we do a mean field, and then we do fluctuations on top of the mean field to derive a topological field theory, right? Now so the universal properties of the state will be captured correctly by the TQFT. But of course, we are doing approximations, right? So in that process, all non-universal information is lost.
I got it. But to put it another way, you're saying, look, actually, suppose I didn't care so much about the underlying Hamiltonian, but I just said this was my ground state.
Exactly, yeah,
And, okay, assume that it's gapped.
that's right, yeah.
Now I can measure the response to an external.
Various external probes, yeah.
And just from the properties of the wave function, I can compute that response.
No. I'm not, the wave function was just to motivate. The wave function was used at 2 stages. First was as a motivation for the field theory, right? For the field theoretic approximation, right? And the second was to motivate a microscopic Hamiltonian, right? So the logic is like this, right? So we start from a model Hamiltonian, we make a guess for the answer, and then we see, can we run with the guess and construct a good effective field theory for a possible phase of the system.
Right. In other words, to put that another way, you guess an answer, and then you say, can I actually construct a model Hamiltonian for which that answer is actually correct?
No. That's not what we're doing. We're saying there is a Hamiltonian. Think about the big space of such Hamiltonians with arbitrary interactions, Vij, and maybe I even want to add, 3-body interactions for V2ij, V3ij, k, and so on, right? Multi-particle interactions. And in this infinite space of Hamiltonians, right, we want to ask, is there a phase of matter which is what kinds of phase of matter exist? And we are seeking a description of a particular kind of phase of matter, which is an SPT state, right? And then I argued that there is, by doing this and then making sensible approximations, which are not energetically controlled, They won't get the mass gap right and so on, but they're, they're stable approximations. You do fluctuations beyond those of the mean field, and it gives you a description of an effective field theory for some state, which is a stable phase of matter, right? So we are then able to describe a stable phase of matter, which is an SPT state with sigma xy equals 2 and kappa xy equals 0, right? And then we go back and then ask, can we make an educated guess on what Hamiltonian in this infinite space of Hamiltonians will stabilize this particular state? And that's where I argued that this simple Hamiltonian works, right? And we check it numerically and it works, right? So now we know that there's a very simple Hamiltonian which whose ground state has all the properties that we expect is correctly described by this approximate field theoretic treatment, right, that gave us a certain topological field theory.
So that's what I was saying. By the time you came to this Hamiltonian, after that at least it was numerical, but there
That's
was
right.
very strong evidence
That's right.
that you had this particular SU2 symmetric.
The evidence is strongest at the pseudo-symmetric point, but then we can move away. It's okay. It exists in a range of this phase diagram.
Okay.
Right.
But let's at least take the SU2 symmetric.
Right,
There you have
right.
very good evidence.
That's right, yeah.
And so there you know that you're getting this kind of topological
Field theory. That's
where
right.
Your gravitational Chern-Simons term was not present.
That's right.
And you had the other one with
Exactly. That's right. That's right.
so
Right. So in other words, the field theoretic treatment, it's very approximate, right? It sort of and you could, for any particular microscopic Hamiltonian, you could say it's totally uncontrolled. Why this mean field? Why not do something else, right? But what it does tell us is that in this infinite space of Hamiltonians, there's some finite range of parameter space in which this phase is allowed to exist. But then to nail down which particular parameter regime it actually exists in, we abandon the field theoretic approach and we do something else. We write down a Hamiltonian, we do numerics, and we sort that out, right? In this case, it turns out to be a very simple Hamiltonian, but it needn't have been the case. In other more complicated phases of matter, it will be some complicated interaction, right? So we know that this phase exists. The field theoretic argument tells us this phase is allowed to exist, right? The numerics tells us exactly where it exists, right? So then we are quite comfortable with the existence of this phase, right? So then we know that it has sigma xy equals 2. There's a phase that exists which has sigma xy equals 2, kappa xy equals 0, and has no exotic excitations in the bulk, right? And we know exactly what long wavelength TQFT describes this phase. And it's precisely this theory, right? It's this theory. So then we can do that path integral thing. Right? Instead of doing calculating the partition function with the original microscopic theory, we just do it with this, right? And then the answer is just what I described here. Right? It's just this guy. Now, the next point to make is that from a certain point of view, all this is totally apparently obvious. So if you ask, so this is a classical field theory right now, right? This induced action is a classical field theory for a Chern-Simons, for a classical abelian U1 Chern-Simons field theory. Now if you ask, when is such a theory sensible as a theory of bosons, right? Now, theory of bosons means you should be able to formulate it on a non-spin manifold. Now, in 3 space-time dimensions, every manifold admits a spin structure. So, non-spin means you don't choose a spin structure, right? So then, with those conditions, K has to be even. And furthermore, the most general thing that you can write down,
that went by me. So every manifold admits a spin structure.
in 3 dimensions, up to 3 dimensions.
Independent of the choice.
Exactly, yeah.
And I thought K had to be, go ahead, okay, so it has to be independent of.
Right, so you can ask what is the most general legal classical Chern-Simons classical topological theory that you can write down for A and G that makes sense.
Oh, I see. You mean if there was a gravitational Chern-Simons term, it would have to depend on that, on the corresponding connection, and therefore the spin structure. Is that what you're saying?
No. So if there is a gravitational, so to complete the story, so the most general such field theory on a non-spin manifold is K over 4 pi integral A dA plus the gravitational Chern-Simons term. Let me just write it as Cs of G. But this coefficient has to be, 16. Or 16 times some other integer K prime, right? Which is exactly what I said earlier, that the kappa xy is allowed to be a multiple of 8. And the 8 corresponds to a theory whose boundary, the edge state is this E8 level 1 theory, right? And then copies of it will give you, yeah. So this is the most general thing that's allowed as a legal classical field theory on a non-spin manifold, right? Now the examples we've constructed here so far have K prime equals 0 and K equals 2. But any even K and K is even. Right? So this is the general thing. So people who knew this probably were not surprised by any of this story, but Condensed matter of physics, we have some way of getting there without.
But just to understand, if we had a fermionic theory, or if there could have been a dependence on the spin structure,
Right.
there is an additional topological quantity you can write down. Is it?
No. So right. So K is allowed to be odd if you have fermions.
Oh, you're saying K even.
That's right. Yeah.
K could become odd. I see. So K has to be even. Let me understand. Sorry, I'm so slow. So the fact that K is even was necessary. I mean, the Chern-Simons theory makes sense for any integer K.
No, but if you don't want it to depend on spin structure, then K has to be even. So
But in the Chern, I mean, in A and D, there's no spin structure, is it? And is that?
no. So the argument is basically one way to argue it. The poor man's argument is the same as what I just told you. So you take the theory A dA over 4 pi, right? And then you look at the monopole operator, which inserts 2 pi flux of little a. Now this guy also has is charged under the U1, right? Now this operator is a fermion, right? So it's a local operator of this kind. This theory has a local operator which is a fermion, right?
That was what you were saying. But you don't want to allow exotic states.
Right. So here we are explicitly, since we don't have exotic states, this response theory, this is a theory, then it just has bosons in it, right? It can't depend on you should be able to formulate it without choosing spin structure.
I think we look at the most general looping Wilson line in this theory. It would not be well defined and without a choice of spin structure.
That's right, yeah.
These Wilson lines are effectively fermionic with respect to each other. If K is odd.
Okay, so you're saying, so another way to say it is, this is actually not totally specifying with Chern-Simons theory. Because I should also tell you how to compute the expectation values of all Wilson.
Of all Wilson
And
loops,
there
yeah.
is spin structure in there.
Exactly, that's right, yeah.
Okay. I see. I wasn't quite understanding that. Okay. All right. Unless K is even. Then-
Unless K is even.
Okay. Thank you.
Yeah, and this K prime is, it's multiplied by 16, right? So,
Interesting.
So we have a simple construction of the states with this guy as well, but you know, it's more complicated than this and less microscopically controlled.
Good place to
Yeah, sure.